Thank you very much, Danny. It's a great pleasure and honor to be here, to be invited here, to celebrate Tu B'Shvat with you, and to show you the fruits of the Israeli fruits that does not grow on trees. So I'll start. Yael talked about students, how great students we have. So it's true, and I'll show you, and I'll talk about one of the students, one story of one of my students, Yoav Golan. He started working in my lab when he was at the first year of his bachelor degree. And now he's about to complete his PhD next year. And he has a dog named Tai. And once he took a course on haptics. Haptics is the science of touch, of communication through touch. And he saw that there are a lot of work on haptics for human. Medical devices and all kinds of devices that humans can communicate through touch. But there are almost no work on haptics for dogs. So he came up with something interesting. But before that, working dogs are used in many applications. Some of them are search and rescue. And search and rescue environment can be very noisy. And it can be hard to command the dog to do something by voice because there is a lot of noise out there and the dog would not hear. So he came up with a simple and interesting solution. He built a vest for the dog with vibration motors inside. Small vibration motors that similar to those that we have on our cell phone that vibrates. And he mounted those vibration motors in the vest, in the internal part of the vest. You see 4 of them. And he built also a pronged housing for those vibration motors in order for the dog to feel better the vibration. And then he built a remote control. And the remote control can command these vibration motors and do different type of vibrations. And you see the remote control, and a few months ago, Yoav took this vest and the remote control to a conference in Japan. So you can imagine how it is to fly with this kind of a remote control and pass through security. But it did pass. So he wanted to understand what the dog can understand and what type of commands and how the dog can infer some of the vibrations into commands. So now the dog needs to feel, to think what it is expected from it to do, and then do it. It's like Pavlov reaction. So we did 4 different commands, spin, down, to me, and back pedal, and we checked different types of reaction. One is the amount of vibration, how much vibration we need to apply. What is the threshold? Where the vibration is being applied? Is it in the front motors, the back motors, the right, the left? And also we did some pulses for the vibration. So the pulses can be changed, the time interval between the pulses can be changed. And therefore the dog can understand that if there is a longer interval, this means different command than if there is a shorter interval. And this is how it works. you see, by a push of a button, now the dog comes to Yoav. And then it gets a treat. And another push. This is the spin command. And another button, and the dog sits. And so on. And another benefit for that is that dogs, when they are trained to follow the commands of their owner, of their person that command them, that train them. But now, not only that person can command them, but also another person, because it's a remote control. It's exactly like we command any other device. So now we have a remote control dog. And this is the interesting thing about this research. So we saw that the dog can understand the haptic commands, the vibration, can understand where the command is applied, it can understand what type of command is expected from it to do, and distinguish between the temporal commands, the time intervals between the pulses. So that was very interesting, and National Geographic featured this research recently, and there were many views for that. But we have not only great students, we have also great collaboration between faculties, as Yael mentioned. And I'll want to show you just one of them through my personal story. In 2003, I was about to finish my PhD. My PhD was about walking machine, how machines can walk, how can they maintain balance and stability and walk here inside tunnel environment, but also walking as in general. So you don't see all the math and the physical things behind this and the motion planning, but there is a lot of it. The interesting thing, and what I want to mention here, and the personal thing, is that 2 weeks before submitting my dissertation, I fell in my backyard. I had a ceramic floor, a wet ceramic floor. I went there and fell back and broke my neck. So you see my backyard there with 2 of my sons. And I had through a surgery, and now my head is connected to my body with 4 screws and metal plate as appropriate for roboticists. But, and if I talk about my sons, so this is my family. You see those 2 sons, small, young sons that were there. Now they're standing next to me in this photo. Yes, one of them is going to get married next month, and the older one is already got married last year. So this led me to be interested in human walking. So the physics and the same principles of walking are the same for machines and for human. And that, my field, led me to get more interest in human walking and how to prevent falls. How to prevent falls as we do in robots, that we prevent falls of the robots. We plan their motion and they maintain balance. So I met Itzik Meltzer, Professor Itzik Meltzer from the Physical Therapy Department in 2007, and since then we're collaborating and working on this subject. But before I'll tell you what I'm what we are doing together, let's see how terrible is the problem of falls. So every 20 minutes, a person dies in the United States from a fall. That's terrible. And 1 out of 3 above the age of 65 will fall this year. And 1 out of 2 above the age of 80 will fall this year. And these are really large numbers. And this is a terrible, terrible problem. So each of us probably know someone who fell or fell by himself, like me. So there is something that we can do. But let's understand how falls happen. Falls happen when 2 things happen. One, there is some disturbance to the walking, some perturbation, something that disturbs us from walking. Either it is an obstacle or something else. And then there is a failure in our postural control system. We need to control ourselves to do the next step fast enough in order not to fall. Sometimes we don't do that, and then we fall. So how we cannot fall? How we can train ourselves not to fall? If we want to train a swimmer to swim, to become a swimmer, then we won't tell him, go run, right? He needs to swim. That's the specific training. Specific trainings mean that we want to cause someone to be good at something, he needs to train in this thing. So if we want to prevent falls, we need to create falls. And this is what we are doing. We are doing a device that actually creates falls in a safe and controlled environment. So no harm would happen. We applied for patent, and this patent was approved and licensed to a company called Meditouch in Netanya, and now it's a commercial product.
Balanceability is essential for the performance of almost every kind of physical activity. Orthopedic and neurologic injury or diseases detrimentally affect this ability. Automatic postural responses must be targeted and practiced through exposure to controlled and customized unexpected perturbation, such as compensatory step practicing. Traditional therapy almost totally ignores automatic postural response training. This is because of safety and technology issues preventing the use of unexpected perturbation. The Balance Tutor System by Meditouch utilizes the clinical power of controlled perturbation and reactive response training, giving clinicians a safe, high-technology solution. The Balance Tutor mimics a real-life challenge as the platform moves in a medial, lateral, forward, and backward direction while the patient is standing, walking, and even running. A harness and stop button are there for safety. The perturbation can be customized to the stance or swing phase within the gait cycle, allowing the therapist to focus on a vast range of clinical indications. The Balance Tutor is used in many rehabilitation clinics around the world, treating neurological, orthopedic, vestibular rehabilitation, prosthetic fitting, sport injuries, and even falls prevention in the elderly. The Balance Tutor is the only CE and FDA certified system that provides safe reactive response training for physical rehabilitation. The Balance Tutor allows you to achieve optimal recovery and improve quality of life.
The system actually moves sideways or accelerate and decelerate. So your leg is not where you expected it to be, and that is a perturbation, a disturbance to walking, and then you need to conduct the next step fast enough in order not to fall. And we have a safety harness such that no harm would be caused. This system was also sold to Real Sociedad, a soccer team in Spain, and they have problem of injuries of players, and they bought the system to prevent, to rehabilitate their players
que se caracteriza por generar perturbaciones
after
inesperadas.
injuries.
Frente a otros sistemas de
As you can
prevención
see.
con los que trabajamos, en los que la conducta del jugador es proactiva, con el balance tutor tenemos una conducta reactiva. Es decir, el jugador reacciona ante una perturbación inesperada creada por la máquina, que puede ser tanto en aceleración, en deceleración, en desplazamiento lateral, que hacen que el jugador necesite desencadenar una serie de reflejos neuromusculares con el fin de generar una buena estabilidad de la articulación y prevenir.
So you probably ask what the connection between such a system to robotics. So what is robotics? Robotics is the intelligent link between perception and action. So each robot does the control cycle of sensing, thinking, and acting. The same thing happened here at this system as well. In the system we have a lower platform and an upper platform, which the treadmill is mounted on this platform. And between those platforms, we have force sensors. And these force sensors can measure the center of pressure, the actual place where the foot is located on the treadmill. And we use this data in order to understand where the person is during his gait cycle. We have also a control system, and we have the gait cycle. And you can see here a simple graph that we get from those sensors, those force sensors, and we can analyze the data of those sensors and understand exactly the same, the phase of the motion of the person. Either it's right foot on the ground, left foot on the ground, either it is a foot flat, where the foot is flat on the ground, or heel strike just before that, and so on. So we can time the disturbance, the perturbation, according to the phase of motion of the person, so we can train a specific motion of the person. Either it's right leg, left leg, either it is his ankle or knee, and that's something good that we can do with this system, and this is the robotic part of the system. Some results, you can see that for a 25-year-old subject to get over a perturbation, to recover from that, it takes 8 steps. For a 65 years old subject, it takes 15 steps, much longer. In a paper that we published, we showed that the actual trigger of starting the next step is happening faster in people that were trained by our system. So it means that training actually improves balance. After training, you actually do the next step fast enough in order not to fall. And this is a source of pride for me, because our system is helping people not to fall worldwide. And that's, I think, a good and important thing.